So Joshua Faulkner is a research assistant professor in UVM Extension and has coordinated the Farming and Climate Change program in the UVM Center for Sustainable Agriculture for the past 8 years. He conducts applied research on agricultural hydrology, soil health, and water quality. Joshua provides technical assistance to farmers and other people interested in soil and water management to build climate resilience. Joshua's program currently manages over 20 edge of field and watershed monitoring stations across the state of Vermont. Joshua, we're really happy to have you here today and excited to learn about your research.
Thanks, Juliana. And I'm excited to be here too, to talk about such a timely topic. Before I get going, I just want to take a moment to acknowledge Lake Champlain Sea Grant as the primary funding source for much of this work. Really appreciative of what they've really enabled us to do over the past couple years, and very excited to kind of use that as leverage and to launch into some other funding sources and more research. Also, I'm just here to talk about the work. It was done by several of us, and the two key people that need to be acknowledged are Ryan Ruggiero, PSS master's student who just finished up in December and actually just published this work. So congrats to Ryan, but he was a big part of this work, as was Don Ross, Professor Emeritus now in Plant and Soil Sciences. So it was very much a team effort, and thanks to those two. Okay, so let's jump right in here. And I know we have a varied audience, so I just want to take a few minutes here up front to lay the groundwork and make sure that we're all on the same page in terms of what is tile drainage, why do farmers use it, and what are some of the most important factors in terms of current research. So let's start with what is tile. So essentially, tile are perforated pipes that are placed underground within a crop field, about 3.5 to 4 feet deep. It's not a new concept to drain agricultural land. You can see a quote there. We knew about the benefits of drainage way back in Cato's time, but the processes or the mechanisms by which we drain a field have changed and evolved greatly. Early drainage was hollow channels dug out in the soil and then covered with rocks or covered with wood and then backfilled. We then moved into clay pipes or clay tile. That's where we get the name for tile drainage. And now we use black corrugated pipe, which you see on the right-hand side of your screen. But drainage has tremendous benefits for farmers. The biggest one is that it improves yields, and it doesn't just improve yields. I think one of the important points there is that it gets farmers off of a roller coaster from wet years to dry years. It levels out those years so that they have some consistency and some level of certainty in what their yields are going to be, which is especially true now in the age of climate change. We don't have a lot of good data on how much it improved yields on Vermont farms. So I'm showing some data there at the bottom of your screen from Ontario, which isn't that far away, but you can see yield increases can be anywhere from 20 to over 40% for some major commodity crops. And then the longest running drainage study that I'm aware of took place in Ohio, and over 25 years it increased corn and soybean yields by 30%. So really meaningful yield increases for farmers. And then perhaps just as important, drainage improves trafficability for farms. And when I say that, I mean, it allows farmers to get into the field and do what they need to do when they need to do it. Drier soils in the spring could mean planting on time. Drier soils in the fall could mean being able to harvest when you need to harvest. for vegetable producers, drier soils in the summer for various cultivation operations, so on and so forth. You can imagine how the timeliness of these operations is a big benefit to farmers too, and then indirectly improves yields. And the other important factor here I just mentioned is climate change. And I take every opportunity I can to show this slide, and this is just showing how we've seen this about a 4-inch increase in average annual precipitation in the Northeast over the past 100 years or so. That's that sloping blue trend line I show on the main figure there. But then when you look at climate district specific data in Vermont, you see, and over the past 30 years instead of 100 years, you really see a much different picture. You see increases of 9 inches in the Northeast Kingdom, 7 inches in the Champlain Valley, 5 inches in southern Vermont. And so you can imagine the challenge what this means for a farmer in terms of crop production, where 4 inches over 100 years, that's multiple generations on the farm. This 9 inches over 30 years, that could potentially be 1 generation on the farm. So that's really challenging for farmers, and they see an impact on their productivity. This is data from the USDA Risk Management Agency that just parses out where and how crop insurance payments were made for what impact. And it's clear that the biggest piece of this pie by far is excess moisture in Vermont. And anecdotally, we don't have data on this, but what I see is that tile drainage is probably the #1 adaptation practice that farmers are using to adapt, row crop farmers, dairy farmers, and some vegetable farmers to adapt to climate change. It's a very important tool in their toolbox. And then it's not a new tool, and I've shown this before. This is a quote from the Vermont's Ag Experiment Station report in 1912. Even then, the value of drainage in a wet climate like Vermont was well known and acknowledged. And this is just an old ditching machine up in horse-drawn ditching machine in St. Albans. The question then is whether one can afford, not whether one can afford to drain, but whether one can afford not to drain. And I think that may hold true today. So even with all those given those benefits to drainage, there's trouble in paradise here. There's obvious cause for concern because of some work that has occurred. I think the researchers in Ohio and the Western Lake Erie Basin first raised this flag and said, we are starting to see phosphorus export from our tiles, and it is raising eyebrows and causing us to intensify our monitoring efforts and take on new research to understand the magnitude of these phosphorus losses in tile. Vermont certainly took notice of that. We've issued new rules that are included within the required agricultural practices around tile drainage, and tile drainage has been, it's a fairly, as agricultural soil and water topics go, it's been a fairly hot topic, I would say, in Vermont over the past few years. But even recognizing that there is phosphorus transport through tile drainage, it's still complicated. There's a great body of literature that indicates that tile drainage decreases surface runoff when we drain a field, and that makes sense. You can imagine as tile drainage reduces the soil moisture, that creates more space for additional rainfall to soak in. So tile drainage has been shown to do that. So we might actually be seeing reduced surface runoff with tile. And then we hear from farmers that, now that I have my field drained, I see less evidence of surface erosion, which is a really good thing. And then Heather Darby did some survey work a couple years ago, and that survey work of farmers indicated that tile drainage was really allowing farmers to adopt many of the best management practices that we're promoting so fiercely for lake water quality, things like no-till and cover cropping. So it's complicated. And then the other two things that I want to briefly touch on before I get into study methods. The first one being preferential flow, this kind of phenomena where we see water moving downward through the soil very rapidly, through whether it's through pores or through cracks. You can see on the right-hand side of your screen, this is a study that was done at my old lab at Cornell, where dyed water was dosed onto the soil, and you can see that it moved initially through the bulk soil, kind of how we would expect water to move. But then there are these streaks down through the soil where it moved very quickly through channels. And I placed a white circle representing a tile drain there, so you can imagine that water, even though we have this all this soil above it, we may still see water moving very quickly to that tile from the surface. And then on the left-hand side of your screen, these preferential flow paths, I believe, are a defining characteristic of the soils of the Champlain Valley. Because they are heavy clays, shrink swell clays, and they do crack, we see we have the potential to see substantial preferential flow in these soils. And that's my size 12 boot beside a crack in the Champlain Valley just this past June. And in that crack, this is an undrained field, but in that crack, we dumped 250 gallons of water in that single crack, and it never filled up. So you can imagine there's lots of space in the soil for water to potentially move quickly downward and possibly into tile lines. And then the other factor I think we need to mention is legacy phosphorus. And this is a term that is coined not that long ago, 5 to 10 years, and has really raised the awareness, much like tile, phosphorus transport and tile. But the fact that there is significant amounts of phosphorus that has accumulated within our soil with additions year over year over year. And much of our work goes into trying to limit the loss of what we call incidental phosphorus loss. So manure on the surface of the soil, for example, that would wash off during a rainstorm. That is where a lot of our management is focused, but yet we have these phosphorus sources in our soil that have built up year over year over year, that we also need to understand the contribution of these in the Champlain Valley. We've seen that it can be significant in some watersheds, but we don't know in the Champlain Valley. And then also, ultimately, what management practices do we need to employ to manage for these sources of phosphorus, not those incidental phosphorus losses? Okay, so objectives of our project were to first establish some long-term paired watershed monitoring stations at the field scale, something that we could use for this project, but then also really build it for the long term so that we could continue to monitor losses and do studies into the future. We then, as part of this project, monitor annual surface and subsurface runoff volumes and P losses at 2 sites over the 2-year project period, which we had a little bit of a hitch with COVID, but we did get solid 2 years of monitoring in. And then we also wanted to increase our understanding of the hydrologic flow paths within the soil related to the preferential flow, and then how that may be functioning in terms of moving that legacy phosphorus, that long-term phosphorus that's in our soil, not just the new manure that is applied. And then beyond what I'll be able to talk about today, and really beyond moving into the future, we'll be evaluating a best management practice and its efficiency at reducing phosphorus losses at one of these field sites. So, and then also taking all these, everything we've learned and incorporating that into the Vermont Phosphorus Index, which is our really our primary tool for evaluating, P loss from farm fields in Vermont. So these, we'll be continuing this work on these last two bullets, and I can come back and talk about those in a few years because they will take some more time. So our experimental design was a typical paired watershed design where we have two areas of a field. This is at the field scale, several acres in size, where we manage them the same. And we do monitoring of flows and phosphorus from those two micro watersheds during a calibration period. Really to understand the natural differences in the hydrology of those two watersheds before we move into our treatment period. And the treatment period is when we would actually change the management on one of those watersheds, on the study watershed, and then evaluate that moving forward, and really being able to attribute any changes we see in terms of flow and water quality to the change in management, because we can really account for the natural differences in the watershed's hydrology because we put in the time during that calibration period. So that's a really important piece of this. So our study sites, all of them were in Addison County. We had one paired watershed study site and one unpaired. So we kind of had an initial site that we had started to work with before the Sea Grant funding, and so we continued to monitor that one through this project. But then we're able to establish this new paired site. Both of these sites had relatively new tile installed in 2017, 2018 or thereabouts. They're heavy clay, typical of farm soils in that part of Vermont. Corn silage was the crop being grown. And we had, I really can't understate the importance of this, a high level of farmer interest and cooperation in these studies. And I'm showing, we really can't do that work without the farmers. So they need acknowledged in this work as well. I'm showing just kind of a generic schematic of how this study was set up. This is not the actual field, but we had two tile networks that were side by side. And then we had that were both monitored at their outlet, and then two micro surface watersheds within those that laid above those tile networks, if you will, and those were also monitored. And you could see the size of our watersheds there and what scale we're working on. Okay, and so the ways in which we performed our monitoring. For our tile lines, we excavated down around the main at very close to the outlet, and installed electromagnetic flow meters on those to measure flows in the tile, but also to provide flow data to our automatic samplers so that they could use a logic based upon flow rates to perform their sampling. So won't get into the details on the logic there, but just to say that we did time-based sampling for base flow. So in that slow flow in between storms, we sampled every 6 hours. We would pull a sip of water and then composite that over several days. And then during the storm events where we have elevated flows, our units would sample based upon how much water has passed the measurement point, so that we get this nice flow weighted sample. For surface monitoring, we used a combination of weirs and the end of pipe, in the end of pipes after water was directed into those pipes. And then we also used H flumes, which are the more traditional way of measuring surface runoff from fields, because of really they can measure low flows and they can measure high flows. They're very good in terms of the range of flows they can measure. And at our surface sites, we use two-part flow-paced event sampling. So just to say, we had one part of the program that would capture smaller events, and then one part of the program that would ensure that we could capture the large events too. So we would hopefully never miss an event, depending on, because it was too big for the smaller program. Okay. And then the other piece to talk about in terms of our methods was that those monitoring efforts allowed us to capture hydrographs and measure phosphorus concentrations. But then once we had those data, we then wanted to try to untangle preferential flow paths and matrix flow paths, and where the water was coming from in our outflow, using some hydrological analytical methods. And so just to kind of pose a couple questions here. The first one was, we wanted to know, what is the water's pathway to the tile line? Was it through preferential flow, or was it through matrix flow, or through the bulk soil? And so those were termed either quick flow or slow flow. And we were able to solve for that to some degree using hydrograph recession analysis. And then we also wanted to know, and very related to legacy phosphorus, what's the source of the water in our outflow? Was it actually new water, the water that comes from that particular storm, that rainwater? Or was it new water coming into the soil and then potentially pushing out old water that had been in that soil, sitting in the matrix for a period of time? I'm showing a little red circle around how that might happen, where we see new water coming in through a preferential flow path, being absorbed into the matrix, and then pushing old water out into that preferential flow path. And so we use a technique called in-member mixing analysis for this, or EMA, by measuring electrical conductivity of various members, the groundwater, the rainwater, the surface water, the tile water, and used a mass balance approach to tease that apart. And using those methods, we were able to essentially break down our total tile flow into 4 different components. So to start here, our big red areas are total tile flow. We were able to divide that into whether that water was traveling through that preferential flow path or through the matrix flow path. And then, was that preferential flow new water from that storm, or was it old water that is being pushed out of the matrix into the preferential flow pathway? And then the same for the matrix. Was this new water coming from the matrix at a very slow rate, or was it old water coming through the matrix at a at a slow rate? All right, and so this is just an example of after this application of the hydrograph recession analysis and the EMA. This is what a storm might look like. The different information we would get from that. The orange line, upper orange line being the overall flow for that storm, and then each of those other lines below it being one of those components. And so this was a really fascinating way to break down our events. And this had meaning in the sense that we knew that our expectation would be that the old water would contain the legacy phosphorus. So if we can break apart this hydrograph into old water and new water, we might be able to understand what phosphorus is coming from legacy sources, or what phosphorus is coming from our incidental sources. Okay, we also wanted to understand the influence of climate change on tile drainage, on tile outflows. And to do that, we aggregated our rainfall data, which was collected using a tipping bucket rain gauge, and looked at pulses of rainfall and what phosphorus concentrations followed those particular pulses of rainfall. So if it was a high intensity pulse or a low intensity pulse, we could then put those in different buckets and look at phosphorus concentrations for each of those buckets. Okay, and now into some results. So looking at annual loads over the monitoring period, I should start this with saying that we unfortunately had 2 very dry years during the course of this study, 2020 and 2021. They had 60 to 73 centimeters of precipitation during the water year. An average would be 100 108 centimeters. So that should be held as a caveat in terms of understanding our loads here. So starting in 2019, we're looking at loads divided by base flow and event, and then also growing and non-growing season loads, the G and the NG. But I'm just going to focus on the totals. At the AHS site, we saw a total during 2019 of about, this is grams per hectare, and that would be about 1.2 kilograms per hectare, roughly equates to pounds per acre, if you think in those terms. In 2020, we had about 1.4 kilograms per hectare, so roughly 1.4 pounds per acre. At the DCN and DCS sites, we saw a little bit lower loads at those sites, 0.8 kilograms per hectare in 2020, and roughly about 0.8 kilograms per hectare in 2020 and DCS as well. And then 2021, loads went up at DCN, total loads went up at DCN, and stayed fairly constant at DCS. And really, this is good information, but I think it's most important to put this in context of what loads have been seen elsewhere. And so I have that across the bottom there. Kevin King's review paper from 2015 is probably the best source of loads from around the country, other studies. And so we're right in the middle of those typical loads seen elsewhere. Air surface loads are shown here in this blue table. 2020, we saw about 1.4 kilograms per hectare at DCN and about 0.182 at DCS, and then those dropped dramatically in 2021 with the drought that we had. So very low surface loads in 2021 because of the drought. Not a lot of water moving across the surface, most of it moving soaking into the soil and then through the tile. So this is what output looked like, and I just show this. These are a string of storm event hydrographs put together, and this shows the phosphorus loads. Zoom is kind of blocking the top of my screen here, but let's see, let me go back there. The primary point that I wanted to make here is that most of the phosphorus is leaving during the storm event itself, that we saw close to 96% of the total phosphorus loads during the storm event, which was very good information. Meaning that those base flow, those low flow periods are moving an insignificant amount of phosphorus. It is occurring mostly during the storm events. And then of interest, I think, is that we also did some nitrogen measurements as well. And at one of the sites during the first year, we saw a total of 111 pounds per acre of nitrogen being lost from this particular site. So you compare that to our total phosphorus loads, which are down around 1.4 pounds per acre. Here we're 100 times greater in terms of nitrogen losses. So we're concerned about phosphorus in the Champlain Basin, and we're more concerned about nitrogen in the Connecticut Basin. But I think there's a lot of work that we may need to do in the future as we think about how to manage nitrogen, and the fact that this represents an economic cost to the farm as well, not just a potential environmental impact. Farmers would like to understand that they're losing this much nitrogen. And we saw a very similar loss the following year, 71 pounds per acre of total nitrogen as well at the other site, at the DCS site. I'm sorry, at the AHS site. Our other finding is that we saw that that concentrations are really driven by flow rates. Meaning that as flow increases, concentrations tend to increase. So our phosphorus export is transport limited, not source limited. There's plenty of phosphorus there if we have the flows to move it. And then we also did see some very concerning high concentrations. These are parts per billion of TP and SRP, and we saw those directly following manure injection. They were very high concentrations, but had very low loads because of low flow. So results of our mixing analysis were that, and I'm not going to be able to show much here except give just some summary points, were that quick flow and new water were really the best predictors of P concentrations during events. And that means essentially that the majority of the phosphorus transport is through preferential flow paths, especially during dry conditions. So we were able to understand that those preferential flow paths were very important in these systems, especially during drought. And we also saw strong evidence that quick flow and new water were not strictly the same water, which is counterintuitive. So this means that there was mixing occurring between the matrix and the preferential flow path during a storm. And we had actually new water pushing out old water, and then old water being measured in our storm flow. And then particulate phosphorus dominates losses during the summer, but only when the soils are wet. And so we focus on the summer here because that's really assumed to be the legacy phosphorus. Most of the phosphorus we see in the summer should be legacy because the manure applications happened almost a year prior. But the phosphorus losses in those summertime periods were particulate phosphorus, meaning that there could potentially be internal erosion occurring, if you will, and soil particles moving into those preferential flow paths and then into the tile. So more work to be done here. And then our rainfall pulse analysis showed that we did see significantly higher flow rates and particulate P concentrations in our tile drain outflow after those high intensity pulses compared to our low intensity pulses. SRP was also higher, but not near as much. And this obviously has cause for concern related to climate change and the more frequent high intensity events we would see with climate change. Okay, I'm trying to finish up here quickly. Our conclusions, so overall our conclusions are that phosphorus loads were really within typical ranges reported elsewhere. Nitrogen losses were concerning. I think an area for more work there. And then our discharge rates, our flow rates really drive overall phosphorus losses, not phosphorus concentrations in that discharge. So that means our phosphorus is transport limited, not source limited. There's plenty of P there. It's just whether we're going to have the flows to move it or not. And then, as you might expect, with cracking clay soils, our preferential flow is much greater during droughty periods when those cracks are open and they can move water to our tile drains. And then finally, our manure injection prior to storm events on dry soils could lead to very high concentrations, potentially increased P losses if we have a storm event following that injection event. So calls for potential additional thought and work here about how we might manage manure injection and judge the risk on that related to subsequent storm events. And then legacy phosphorus losses may be driven by particulate phosphorus originating within the soil profile. So maybe our phosphorus is moving from within the profile, not across, or particulate phosphorus moving from within the profile down within those preferential flow paths, eroding the walls of those flow paths, and not from the surface. And like I said, climate change also poses a risk for increased phosphorus losses in tile drains, not just in surface runoff. We've known it poses a risk in surface runoff for some time. A few references, including Ryan's paper. Congrats to him again. And now I think we have a good 20 minutes or more for questions.